Hello students. In the previous lecture, we have seen how is the behavior of current when we apply the alternating EMF, when we connect alternating EMF to resistance, to inductance and to the capacitance. First we applied the alternating EMF to resistance, then we applied it to inductance and we applied to capacitance. And we have seen when we connect the alternating EMF to resistance, the voltage and the alternating the current both are in phase. We have seen when we connected the alternating EMF to inductive load or inductance, we have seen the current lags and the EMF leads. And likewise, in case of capacitor, we have seen the current leads by pi by 2 to the alternating EMF. There is a small portion that is remaining as connected to this capacitive reactance and inductive reactance. So we have seen that day that the capacitor and inductance both offer the resistance. Capacitance and inductance both offers the resistance to the alternating current like the resistance. That means we know the resistance which opposite to the current. Likewise, there is inductive reactance, there is capacitive reactance. This reactance also opposed to the current, and we know the unit of this XL and XC is ohm. Unit of XL and XC is ohm. And what are the formula for XL? XL, that is inductive reactance. That is inductive reactance equal to omega L. That is 2 pi f into L. Okay, so omega is 2 pi f. So XL is equal to 2 pi fL, and this portion is called as inductive reactance. Okay, this is the resistance which inductors offer when the current passes through it. We know that it opposite to the change in current. Likewise, we are saying now, so this is number 1. Number 2, that is XC equal to 1 upon omega C, that is 1 upon 2 pi f C. Okay, so this is called as capacitive reactance. Basically resistance, inductive reactance and capacitive reactance, all the three are the resistances which opposes to the alternating current. And if we look at this equation, XL is directly proportional to frequency. That means if we increase the frequency, XL will increase. That means if we increase the frequency, the resistance of the capacitor, the resistance of the inductance will increase. If we lower the frequency, the inductive resistance or inductive reactance will decrease. That means XL is directly proportional to F. XL is directly proportional to F. Okay, and look at this equation. X is equal to 1 upon 2 pi Fc. That means Xc, that is capacitive reactance, is inversely proportional to frequency. It is inversely proportional to the frequency. Means as we increase the frequency, capacitive reactance will decrease. As we decrease the frequency, Xc, that is capacitive reactance, will increase. That means Xc is inversely proportional to frequency. And in case, say frequency equal to 0, in case of DC, frequency equal to 0, because frequency comes to the picture unless there is a alternating voltage. Okay, you don't see any frequency. So for the direct supply, for the direct current or the voltage, F is equal to 0. So if I put F equal to 0, Xc will be like infinite. Xc will be infinite. It will offer the infinite resistance to the applied voltage. So when F is equal to 0, this is in case of DC. So that means what? That means capacitor do have a tendency to block the DC. capacitor do have tendency to block the DC, because when F is equal to 0, in case of DC, in the direct current, okay, the graph of direct current is like this, okay. So F is equal to 0. When I put F equal to 0 here, okay, so 1 upon 0, that is infinite, so X will be infinite, so it will block the DC. So it will allow only the AC to pass through it, because when we apply AC, that means there will be some frequency, and as the frequency is there, we'll have some finite value of XC. Let us plot one graph of XL and XC. Suppose on the x-axis I put frequency, on the y-axis I put the XL and XC. XL and XC. Okay. Now we know that in case of inductive reactance, as we increase the frequency, XL will increase. So graph will be what? Graph will be the straight line passing through the origin. Straight. Okay. As we increase the frequency, XL is increasing. Whereas in case of capacitive reactance, okay, it is inversely proportional. So graph will be like this. Graph will be like this. Now look at the graph, the nature of the graph. When the frequency is less, X is high, and as you go on increase the frequency, okay, the magnitude of that XC will decrease as it is inversely proportional. We know that the unit of XC and XL are ohms. So basically, we can summarize like this: the inductive reactance and the capacitive reactance are basically the resistance offered by the inductance and capacitance, and there is a difference between resistance, pure resistance, and the capacitive and inductive reactance that we are going to see right now. So I'll erase this. Now, what is the difference between the pure resistance and the resistance offered by XC and XL? That we are going to see now. See, there is resistance and unit is ohm, and there is inductive reactance and capacitive reactance. Inductive reactance is represented by XL and this one is XC. See, though this XL and XC behave as a resistance in the circuit, there is a difference between XL and XC. This resistance is not depend on frequency. It is independent of the frequency. We know the resistance, you know formula, R is equal to rho L upon A. That means the pure resistance depends on what? Is resistivity and the length of the conductor and the area of the cross section of the conductor. Whereas this inductive reactance XL is depend on what? It depend on F. It is directly proportional to F rather. And the XC also depend on F. We know it is inversely proportional to frequency. So resistance is not dependent on the frequency, whereas this reactance, inductive reactance, is depend on frequency. And capacity also depend on frequency. Okay, and it is inversely proportional rather. Okay. Now there is one more difference between resistances and this inductive and capacitive reactances. In case of resistance, it produced heat. Okay, and this inductive reactance does not produce heat. Means when you pass the current through this resistance, okay, heat is produced because of I square R, okay, and in case of this XL and XC, okay, it's independent of the heat, okay. Heat is not produced when the current is passed through inductive reactance and capacitive. This is a basic difference actually. It is not very big point. So XL and XC, they are just like resistances, but they do differ with the pure resistances in case of frequency and in case of heat. I will explain the graph again. This is the graph of XL and XC. As you increase the frequency, okay, the XL, that is inductive reactance, will increase. So graph is a straight line. I will put it XL here, okay. And in case of capacitance, okay, it is inversely proportional. XC is inversely proportional to frequency, 2 pi FC. That means XC is inversely proportional to frequency. As you increase the frequency, XC will decrease. Okay, so graph is like this. So this is all about the inductive reactance and capacitive reactance and the difference between resistances and inductive reactance and capacitive reactance. Now we are going to see what happens when we pass the alternating EMF through the LCR circuit. So let me remove this. So the next topic is AC through LCR circuit. LCR circuit is inductance, capacitance and resistance. So let me draw here. Okay, this inductance, capacitor and resistance, and we'll connect the alternating EMF here, E equal to E naught sin omega t. The symbol of alternating is like this. This one is L, this one is C, this is R. In the previous lecture, student, we have seen the nature of current in case of inductance, in case of capacitance and in case of resistance. Okay, in case of resistance, it is in phase. In case of resistance, the applied, suppose this one is ER, okay, then the current flowing through the resistance R is in phase. Okay, in case of capacitance, the EMF lags and current leads. EMF lags, so I'll put it like this, EC. Okay, and in case of inductance, this EL will lead and the current will lag, and all are lead and lag by pi by 2. Suppose we'll take one case here, that is when EL is greater than EC. When EL is greater than EC, so what will happen? This portion will be, this vector will be like this: EL minus EC. Now we are going to see what will be the resultant E. What will be the resultant E here. Okay. Now we know that in series circuit, current is same. In the series circuit, I will be same, and there will be drop across this inductance. That drop will be I into XL. Okay, and the drop across the capacitance will be I into XC. Okay, and the drop across the resistance will be what? It will be I into R. This particular thing we have already discussed in current electricity chapter. So you are aware in case of series circuit, current is same and voltages are different. In case of parallel circuit, okay, voltage across all the branches are same and the current get divided. So let us calculate the resultant E over here. Okay, so I will draw the vector diagram here. So I will connect this and I will find out the resultant E here. Okay, so E will be E square. Okay, E square will be equal to E R square plus EL minus EC whole square. EL minus EC whole square. Okay, so E will be E Now let E will be equal to what? E will be I into R. It will be I into R. So I R square plus I will replace EL with I into XL minus I into XC. Okay, whole square. Okay, we'll take out the I square outside. So inside there will be R square plus XL minus XC whole square. Okay, so if I take out the root of this, so E will be equal to I in bracket R square plus XL minus XC whole square. Okay, so now I'll remove this. Okay, this is right. So finally we have got the equation that E equal to I in bracket R square plus XL minus XC whole square. Okay, so you can compare this equation with B equal to I into R. So here V is replaced by E. Okay, I is replaced by this R. So now this under root R square plus XL minus XC square is called as impedance. Is called as impedance. So E I, and I will replace this R square plus XL minus XC square. Basically, this R square plus XL minus XC square, this particular thing is the total resistance offered by the LCR circuit. I will tell you again. This total resistance offered by LCR circuit is under root R square plus XL minus XC square, and this particular thing is called as impedance. That is impedance. That is impedance, and it is represented by Z. So Z equal to under root R square plus XL minus XC whole square. So Z is called as impedance. So what is impedance? Impedance is the total resistance offered by the combination of resistance, capacitance and inductance. It is called as impedance. Now maybe in some circuit, okay, the XL is 0. In case of XL is 0, what will happen? Z will be equal to what? Z will be equal to R square plus XC square. Okay. In case of say XC equal to 0, then what will happen? In case of XC equal to 0, then Z will be what? Z will be under root R square plus XL square. So in any case, the combination of resistance and capacitance, the combination of resistance and inductance, okay, is the impedance, and impedance is represented by Z. Okay, so this is all about the impedance. So far we have seen the inductive reactance and the capacitive reactance. So what is the difference between inductive reactance and capacitive reactance and the impedance? XL is inductive reactance, XC is capacitive reactance, and Z is impedance. So basically Z is the combined, the total resistance offered by LCR circuit or LC circuit or LR circuit is called as impedance. It is combination of resistance and any other inductive or capacitive reactance. Okay, now we'll move ahead. Now we'll erase this one. So now suppose the angle between this I and E is phi. Then we have tan phi equal to what? Tan phi equal to opposite side, okay, upon the adjacent side, that is EL minus EC upon ER. That is I into XL minus I into XC upon I into R. Okay, so I cancel, and we have phi equal to tan inverse of XL minus XC upon R. So phi will be equal to tan inverse of XL minus XC upon R. Now look at this vector diagram. You can see that EMF leads the current. EMF leads the current by angle phi. Okay, so I can write like this. So I can write I is equal to I naught sine omega t minus phi. Why minus phi? Because we are seeing that I is lagging behind the EMF, that is equal to E naught sine omega t. Okay. Now what will happen in case suppose condition 2, in case xc is greater than xl, xc is greater than xl, then what will happen? This particular vector will go downside. Okay. In that case, the phi will be leading. So I will be equal to I naught sine omega t plus phi. This is when xc is greater than xl. Okay, or I would say EC is greater than EL. So in this case, the I will be equal to I naught sine omega t plus phi. In previous case, it was I equal to I naught sine omega t minus phi. Okay, so combinedly I can write here, student. Combinedly I can write here. That is I equal to I naught sine omega t plus minus phi. Why plus minus phi? Because in Lcr circuit, sometimes the XL will be high and XL will be high and XC will be low. Okay, and sometimes XC will be high and XL will be low. Okay, so there are two conditions. When XL is high, okay, XL is high means EL is high. When EL is high, the equation will be like this. When EC is high, the equation will be like I equal to I naught sine omega t plus phi. So combinedly, I can write I equal to I naught sine omega t plus minus phi. So this is the current equation in case of LCR circuit. Student, numericals are asked in the examination based on LCR circuit. Resistance of the resistance is given, then the frequency is given. So you have to convert the inductive reactance, that is the XL. Okay, X is equal to 2 pi f into L. If frequency is given, the inductance is value of inductance is given. You can find out the XL, and the unit of XL is is ohm, and the unit of impedance is also ohm. Unit of impedance is also ohm, and the XC, that is 1 upon 2 pi fc. Okay, so in the numericals, the value of the C is given, the value of the frequency is given, and once you know the value of f and c, you can calculate the value of xc. Once you have calculated the value of xl and xc, okay, you can put these values in this equation, and you can find out the value of z. Okay, value of z is what? Z equal to under root r square plus xl minus xc whole square. This we can find out the z. Okay, put the value of z in the equation, you can find the value of E, that is alternating EMF. So this is all about the Lcr circuit, student. Okay, we have seen, I repeat again total topic. First we have seen the graph of XL and XC. Okay, then we have seen the difference between the resistance and inductive reactance and inductive capacitance. Okay, and then we have started the portion that is AC through LCR circuit. Very important topic. AC through LCR circuit means inductance, capacitance and resistance are connected in series, and we have applied the alternating EMF, and we are seeing the vector diagram of these three elements. So we are seeing that in case of resistance, the alternating EMF and the current are in phase. In case of inductance, okay, we have seen the inductance current lags and the EMF leads. Okay, in case of capacitance, we have seen the current leads and the voltage lags. Okay, so combined vector diagram is like this. So we have calculated, we have find out the resultant E. Okay, so total E will be equal to R. Total E will be equal to I in under root R square plus XL minus XC square. Okay, it varies. XL minus XC, sometimes EC will be high, or and EL will be less, so you can change it accordingly. And then we have seen the angle phi, that is tan inverse XL minus XC upon R. and then we have found out what that is I equal to I naught sine omega t plus or minus phi. Why plus or minus phi? Sometimes EL will be higher and EC will be less. Sometimes EC will be high and EL will be less. So accordingly, the combining equation will be I equal to I naught sine omega t plus minus phi. Okay, and the unit of this impedance is Z. What is impedance? I repeat again. What is impedance? Impedance is the total resistance offered by the resistance and inductive reactance and inductive capacitance. Okay, the Z may be the combination of R and XL. Z may be the combination of R plus XC. Z may be the combination of R plus XC plus XL. Okay, not direct addition. Actually, it is like this: under root R square plus XL square, R square plus XC square, or under root R square plus XC square, and XL minus XC whole square. Okay, so Z is the impedance and the unit is ohm. I hope, student, you must have understood today's topic enough for today, and next time we are going to see the LC circuit. Okay, in the circuit, if there is no R, if I remove R, what remains? It's the LC circuit. It is the LC circuit. So in the next lecture, we are going to learn LC circuit. So enough for today. Next time next lecture. Thank you.